I have here on the whiteboard a summary of a number of the tools and kind of problem solving starting points associated with energy. So this may be very useful. I've included, or I've started here with the definition of work or a formula for work by a constant force along a straight line displacement, but including the possibility of an angle because that is sometimes needed. The big centerpiece of this is work is equal to a change in energy. And then the new concept we're going to have in this topic is energy conservation, although more specifically, this formula E initial is equal to E final is applied in situations where we can claim mechanical energy conservation. So we're going to have to distinguish just like big concept energy conservation versus a little bit more specific mechanical energy conservation. And these three formulas here are kind of the three formulas for the mechanical energy forms that tend to come up in this course. So we've got the kinetic energy, we have gravitational potential energy, and we have the spring kinetic energy, and that's 1/2 mv squared, mgh, and 1/2 k x squared, respectively. So the general rule, though, is if you have non-conservative forces like friction or drag, you're pretty much going to have to use W equals delta E. But if those are not there, and you're looking at a system that doesn't have any other kind of force doing work to it, in other words, if you defined your system in a way that it is close to that, then you can use this. And this ties in on the key concepts page to what's stated here for mechanical energy conservation. Mechanical energy is conserved in a closed system that has no internal friction or drag forces. I have above that here a general statement that a lot of this concept of energy conservation, including mechanical energy conservation, is based on, is the idea that energy is neither created nor destroyed. So if it's not created or destroyed, for a particular system, the only option is it can either leave the system or energy can come into the system. But when we say it's a closed system, we're removing that as a possibility. But it can also transform between one form and another. And if it's mechanical energy transforming into thermal energy, that turns out to be problematic. We've seen some examples of that. That tends to happen when there's internal friction or drag forces. So removing that possibility, now we have a very powerful set of problem-solving tools in the form of this concept, same formula that's down here, and these three formulas. I want to mention I could have also put here, some textbooks include a broader statement for energy conservation, which kind of is related to this. It really is the energy is neither created nor destroyed. But you can also say energy is conserved in a closed system, period, without any conditions. But that doesn't necessarily lend itself to problems because, again, this issue of mechanical energy converting to thermal energy. So the more useful statement is this statement about mechanical energy conservation. So really, you should maybe put in your notes or think about this formula not just being initial energy equals final energy where anything goes, but it really should be associated with mechanical energy conservation so that when you start putting in stuff for these two things in a problem, it's only mechanical energy forms that come into it. That's where it really tends to shine and give us really good results in terms of answering questions.